Hey guys, Mr. Brown here. This presentation is going to be about astronomy for the astronomy unit in Science 110. Now, with all that said, let me start by saying that for the astronomy unit, I really do keep things kind of basic. I think it gives you a little bit of a break here in the hard part of the semester. And the thing about astronomy is it is not listed in your course, in the course description for this class. The course description says that we should teach students and you guys should learn a little bit of the ins and outs of kind of the three major physical and natural sciences, those being chemistry, physics, and biology. And you can kind of see that from the way that I've structured the course. But um, astronomy, the study of space and planets and stars and comets and asteroids and stuff, is considered really a subset of physics. And in a way, it's really kind of where physics was born. Some of the first thoughts about physics and the world around us was performed by none other than Isaac Newton when he formulated his laws of gravity or theory of gravity. And, furthermore, astronomy has been a central part in the development of science overall. People have long, for thousands of years, looked up into the heavens and tried to establish some meaning for what they saw going on, figure out why the different bodies and objects that they saw in the sky moved around to different positions. And so astronomy and the study of space has influenced science maybe more so than any other topic, even though we haven't been able to get up there into space, but for about 60 years now. So even though a lot of the stuff that astronomy covers is hard to study or hard to physically touch and manipulate, the overall development of science has really has a lot to thank the field of astronomy for. And so in this presentation, I don't really get into a lot of the specifics because astronomy is such a broad field. I could spend obviously you could spend a whole class doing it. We offer a class here at Sandhills that is just astronomy. And if this is something that interests you, I really would encourage you to go and maybe consider taking that course. Our physicist, Dr. Morse, is very, very intelligent when it comes to the telescopes and looking at the night sky. And you can really, really learn some cool stuff and really get to see some cool stuff in that class. Astronomy is something that I it's one of those things that's filled with a lot of wonder for me. I don't claim to be an astronomer. I've taken a few classes, but some of the astronomy that people are doing today is very, very math intensive, and I don't really claim to know a lot of that, but I know some of the basics, and I do know I've picked out some topics over the next couple of slides that I think are worthwhile talking about, and things that people should just generally have a pretty good idea of concerning astronomy. And so I wouldn't say that this is a very intensive lesson. I try to really keep some things in there that are just interesting. I hope the next couple of slides are just really interesting for you. You'll see that reflected in the assignment for this week. It's not as long as usual, but unlike others, there are a few sections where I've asked you to write a little bit, to have a little bit of a discussion about some of these topics. And I'll actually give you the answers to the questions through my discussion here. So if you just follow along, you'll kind of get those as you go. So one thing I've learned over the years is to kind of start simple with this astronomy stuff. In the past, I've made assumptions that people would have this background stuff. And then I realized that, I'll be in a class and a couple of students will have an idea of what I'm talking about. So I really um, start from the beginning here. So, and if some of this is really just, well, obviously we learned this in third grade. It may have been a while from some others. So this is where we're going to start. We're going to start at the solar system. Um, so we live on planet Earth, and you can see, and planet Earth is part of a system of planets that orbit or revolve around a star we call the sun. And we are certainly not the only solar system in the universe, not even our own galaxy. And we'll get into that later on in the discussion. But this is what ours looks like, and really no two or three are the same. And in this picture here, you can see Earth is the third planet from the sun right here. And you can watch it as it rotates or revolves, is a better word, revolves around the sun. And then you can see all the other planets that are members of our solar system. Closest to the sun, we have Mercury, and then next we have Venus. Earth, as we said, comes third. Mars is the fourth planet. And those are the four interior planets. They are generally smaller in size and rocky in composition. And then after Mars, you have a small region called the asteroid belt, where we have a lot of just rocks and materials that are kind of out there floating in a circle, much like the planets do. Beyond the asteroid belt, we get to the gas giant planets, and these are much, much larger planets made out of mainly hydrogen, helium, methane, and ammonia, and other gases. And the first one that you encounter after you get out of the asteroid belt region is the biggest, Jupiter, and he has the red, colorful stripes that you see in those pictures. After Jupiter, we have Saturn, well known for its beautiful rings. And then behind Saturn, we have Uranus and Neptune, which are smaller gas planets. They have a very distinct blue color. They're often called sister planets because they are so similar. And then on this particular graphic, you'll see this little guy. He doesn't quite share the same orbit as everybody else, but what this is a smaller rocky planet at the very, very outside of our solar system, or what used to be called a planet. If you're of a certain age, you remember learning about Pluto in elementary school being the ninth planet. Well, back probably about 10 or 15 years ago now, they decided, they got together, the astronomers who controlled these definitions, I guess, they got together and decided that Pluto no longer fit the current definition of a planet. It's too small. And so Pluto kind of lost its planetary status. But for those of you who were taught that Pluto was a planet in elementary school, it's a fun joke to make, right? We don't want to forget Pluto. We learned a lot about Pluto. So for those of you who may be of a younger age, you may never heard of Pluto, or maybe you've heard of the controversy surrounding it, but I did learn Pluto was a planet in grade school. So I like to see Pluto included on the animations and stuff, even though it's considered a planetoid these days. All right, so in this slide, we are going to point out a couple of characteristics of Earth's orbit. So the word orbit, or the phrase Earth's orbit, generally refers to the path that the Earth takes around the sun. So in case you are not aware, this amount of time, so the time it takes for the sun to go around, or the Earth to go around the sun one full time, is what we call 1 year. That's how we measure the length of a year. It takes approximately 365 days. It really takes 365 and 1/4 of a day. And so to make up for that 1/4 that we lose every year, we have leap year every 4 years. We have to add that extra day to make up for that time and keep our calendars in track. If we didn't do that, if we didn't make up for that quarter of the day after hundreds and thousands of years of not doing that, all of a sudden it would be summertime in January, after that error caught up to us enough. So that's why we add the 4th day on the February 29th every 4 years. So Earth, you can see it travels in a almost circle. If you can't really tell, this is not supposed to be a perfect circle. Earth's orbit or Earth's revolution around the sun is very, very circular. It's almost a circle, but it's not quite. We say that it is an ellipsis because it's kind of a squished circle, just ever so slightly elliptical path around the sun. And so I want you to notice a few spots on this chart. You'll see that we have this point here labeled the aphelion. The aphelion, which happens on July 4th, incidentally, is the day that Earth is furthest from the sun. Now remember, because this is not a perfect circle, as it comes to this side, you can see it's a little bit further from the sun than it is over here. So at that point right here, furthest away, when the sun sits furthest away from the sun, we call that the aphelion. And you may notice that actually happens in the middle of summertime for us. So try to think about that for a minute. Try to keep that in mind. Summer happens when the Earth is furthest, or summer in the northern hemisphere, rather, I should say. Summer in the northern hemisphere happens when the Earth is furthest from the sun. And then conversely, we also have the perihelion on January the 3rd. And the perihelion is, you can probably guess, the point when Earth is closest to the sun in its revolution. And you can think about this one for a minute too. When we're closest to the sun, the northern hemisphere is actually experiencing winter. You may notice the equinoxes and the solstices on the diagram as well, and I'll get further into those after we have a little bit of discussion about the tilt of the Earth. Before we go further into the discussion about the Earth and its revolution around the sun, I want you to understand, you probably already do, but in case not, I want you to understand that on its path as it travels around the sun, the Earth does not sit neatly straight up and down. The Earth is, as we say, tilted on its axis. So if we had a line that ran straight through the north and south poles, you can see that that line is not perpendicular to the 90-degree here. And the Earth actually spins around this way, just like this, because of that tilt on its axis. That is important for what we're getting ready to talk about here in just a second, how the seasons come about. So this slide here shows what the tilt kind of does to the Earth as it's pointed at the sun. In this image, you can see that because of the tilt, the northern hemisphere, which is, if we kind of look maybe about right here, would be the northern hemisphere, here and up, is tilted more directly at the sun than the southern hemisphere. So as the sun rotates around its axis, the northern hemisphere has more direct sunlight, and it has longer days because the land is more exposed to sunlight because of that tilt. So the longer days happen in the northern hemisphere in this orientation. Even some of the very northern parts, you can see the North Pole and areas close to the North Pole would be completely bathed in light all day long in this orientation of the Earth. And so, and that does happen if you go to, if you get above the Arctic Circle near the summer equinox. The the sun never sets. You can sit up here and as the world spins, it's always pointed directly at the sun, and so you get 24 hours of daylight in the height of summer at the North Pole. Conversely, at the South Pole, you can see it is completely bathed in darkness at this time. And so at the South Pole and Antarctica and all, if you were there visiting at this time when the Earth was pointed at the sun in this manner, you would never see the sun come up. You have a couple of weeks there where you don't see hardly any daylight at the South Pole or in Antarctica. If you do, it's maybe an hour at most. So interesting stuff there. And so now we can bring it full circle. I find this funny. One of the things I've learned along the way in my study of science education is that there was a research study done, and there's a video of it on YouTube. I think you can find that was they interviewed Harvard graduates, and it's a pretty old video. I want to say it was like 1995 now, but they interviewed Harvard graduates on their graduation day. Somebody took a camera and a note recorder or whatever, and went around on Harvard at the Harvard graduation and asked folks, could they explain? These are all decidedly smart people if they're matriculating from Harvard University, but they asked them, could they explain why the Earth had different seasons or what caused the change in the seasons? And only something really kind of surprising, like 22% of the people could explain what caused the seasons. And so you guys are going to be able to explain what causes the seasons if you'll listen up real quick. The most common wrong answer was that the sun gets, or the Earth, excuse me, the Earth gets further and closer to the sun during its revolution. But like I said, that does happen. The Earth does get closer and further away from the sun, but it's actually the opposite of what you would expect here in the northern hemisphere. We are closer to the sun in winter and further from the sun during summer. So that can't be the cause of the seasons. We just talked about the tilt of the Earth and how the Earth faces the sun. And on that last side, we looked at, well, if the Earth is tilted this way, at some point, the northern hemisphere is pointed more towards the sun, and the southern hemisphere would be pointed kind of away from the sun. And you can see that effect here in this part of the diagram. And so because of that, we have summer in the northern hemisphere is getting much more sunlight. That sunlight is lasting longer, and that sunlight is more direct. So we're getting much more sunlight here and much less sunlight here. And that would make it summer in the northern hemisphere and winter in the southern hemisphere. On the opposite side of the rotation, because the tilt of the Earth doesn't change very much, once it moves all the way around here a couple months later, now the opposite is true. The southern hemisphere, because of the tilt of the Earth, is now bathed in much more direct light from the sun, and it's receiving much longer periods of time. The days are much longer for the southern hemisphere, making it summertime in the southern hemisphere and wintertime in the northern hemisphere. Now, you may be getting to the point where you realize that these positions here are what we call equinoxes. So during the spring and autumn equinoxes, there is a point where, because the tilt of the Earth doesn't change very much, as it gets to this point right here and this point right here, there's a point where the northern and southern hemisphere are getting the exact same amount of light all day long, and they're getting about the same direction of the rays. So everything is very equal. And that's what we refer to as the um, spring and autumnal equinoxes. This slide here just gives a little bit bigger diagram of what it would look like, or how the Earth's tilt affects how much sunlight and the directness of the sunlight based on its position in front of or around the sun. In this picture, you could see it would obviously be um, winter in the northern hemisphere and summer in the southern hemisphere. I had to think about it a little bit. And you can actually see that this is how we define the Arctic and Antarctic circles. So if you look on a map, you ever look on a globe or a map, you'll see the Arctic and Antarctic circle outline. And what that is where you get those days of complete light or complete darkness, depending on the position of the Earth around the sun. And so here we have a map. Because of this, you can kind of guess that as you get further in latitude, as you go further north, you would get longer and longer days in the summertime. In the wintertime, you would get shorter and shorter days. It would be the exact opposite. But this map shows when the Earth on the summer solstice, which is the longest day of the year in the northern hemisphere, the Earth is tilted in a position so that it is tilted directly at the sun, or the northern hemisphere is tilted directly at the sun, and it's receiving a lot of light. And like we just talked about, the Arctic Circle would start here, and so this area here, because it's tilted toward the sun, as it rotates around and around and around, the sun never sets. It never gets out of the path of the sun. And as you go further south a little bit, you can kind of see so here you would start to get where it went around the backside and escape the sunlight for a little bit. You would get somewhere between 20 and 24 hours of daylight. So you would only see somewhere between 1 and 4 hours of darkness that night. And as you get up into the actual part of Canada and Alaska, where people or civilization kind of starts to build, you can see that some of those folks experience days that are as long as 18 to 20 hours sometimes. So in the summer, they may only get 4 hours of night of actual darkness. And I've heard from others that even when they say it's dark, it's actually not very dark. It's still kind of almost a twilight outside. I'd say it's kind of hard to say. It's very hard to sleep like that. Hard to fall into a sleeping pattern. And as you go further south, you can kind of see, and us, we're a little bit on the line, I guess, here. If we're taking Moore County, we're kind of in this more not quite orange section, or not quite dark orange section. So it says we should get somewhere between 14 and a half to 15-hour days in the summertime based on our position. On this slide, I have something I personally just find kind of neat and decided that I would talk to you about, really, is the tropic line. So if you've ever wondered why we call these the tropics, or what the word tropical means, the tropics refers to an area of Earth between the two lines that you see here. What those lines represent is where the sunlight hits the Earth directly, so where the sun is directly overhead. And on the winter solstice, it's directly overhead down here at the Tropic of Capricorn due to the tilt of the Earth. And then as it tilts the other way, as it comes around the sun and is pointed in the other direction, the sun's rays are directly overhead at the Tropic of Cancer, yes. So as the tilted Earth moves around the sun's rays point directly at some region of space in between these two lines that we call the tropics. And because the sun's rays are so direct over these portions, you probably know that these are generally very hot areas, humid. It doesn't very often get anything like snow or anything in these areas. You can see this is actually a picture here. On the next slide, we'll talk about how the Earth does actually move just a tiny bit in different ways as it moves through the solar system. But because of that movement, those lines actually move a few meters every year. They move back and forth a little bit, really. And I think this is a picture from Jamaica, I want to say, when I looked it up. And they show exactly where the Tropic of Capricorn is every year as it drifts a little bit. On this slide, you can see some of the extra movements that Earth makes. We probably already know that the Earth rotates on its axis like you see here. But not only that, but it also undergoes a movement called precession that you can kind of see here. And one of the best ways to describe that is that it wobbles much like a top does if you spin it and set it down on a table or something like that. This wobble takes 26,000 years to complete, so this is a very, very slow wobble. And the other movement that the Earth makes is called nutation, and it's kind of hard to see because it's moving with the precession and everything. I almost wish they would show it just in the rotation. But what's going on with the nutation is that the axis is actually rocking back and forth a little bit, so it's going lower and higher and lower and higher. And that's the reason that the Tropic of Cancer and Tropic of Capricorn moved that we saw on the last slide. That movement to go all the way down and back up to rock one time, that one only takes about 19 years. So that's why we see the tropic move every couple of years. And then once it reaches the bottom or the top, it will rock back, and those lines would move back over the same spots. Up to this point, we've neglected one of our closest friends in the solar system, and that is the moon. We can see the moon here. The moon revolves around the Earth as the Earth revolves around the sun. And one interesting thing about the moon is it rotates in the same speed as the Earth. So the side of the moon that we can see at night is always the same side of the moon. As the other side rotates away, we never really get a visual of that side. And so the idea of the dark side of the moon is a true one. We've never seen with naked eyes that side of the moon. So a lot of times in astronomy class, when you talk about the moon, you'll study the phases of the moon and figure out where it's at around Earth to look like either a crescent moon or a full moon or a new moon, et cetera, et cetera. I'm not going to spend a lot of time on that, but there is something about the Earth and moon system that I do want you to understand. The moon is the cause of the tides, the ocean's tides, high tide and low tide on planet Earth. So the moon, as we've established, is rotating around the Earth. And the moon is, relatively speaking, a rather large body. It's large enough that it has a sizable gravitational effect on planet Earth. So the gravity of the moon pulls on some of the things on planet Earth. And one of the things it pulls on is the water in the ocean. So wherever the moon is around the Earth, the water on Earth is tried to be pulled in that direction because the moon's gravity is pulling it that way. And as you can see, that causes kind of a bulge in the oceans all the way around the Earth. And we have thin sides where the moon is not parallel with the Earth and thicker sides where it is. And in these regions, it would be high tide. And in these regions, it would be low tide. Now, you can actually have two different types of tides. And so when the sun and the moon and the Earth are all lined up such that high tide is when the sun and the moon are lined up, you have bigger tides and more drastic tides than in the situation where the moon is perpendicular to the sun. And so in this case, the sun's gravity is pulling one way and the moon's gravity is pulling that way. The moon usually wins out. The sun is much, much bigger. It has much, much, much more gravity, but it is so much further away that the gravitational effects of the moon are felt more so than the sun. And so high tide still points toward the moon, but the sun kind of dampens it. Whereas in this diagram, the sun adds to it. They're both pulling in the same direction, causing bigger swings of the tides. These are called spring tides. These big, big, big swings in tides are called spring tides. And these smaller tides where you don't get much change at all are called neap tides. That's all for all you beach lovers out there. All right, guys, we're getting there. So here on the uh, here on this slide, we have just some facts and figures about the four inner planets as you move away from the sun. They go in order: Mercury, Venus, Earth, and Mars. And I've just listed some um, defining characteristics of each of the planets, and you can read through them here. Most of them are self-explanatory. Um, one of the questions you're asked is, is Venus is the true or false? Venus is the hottest planet, even though it is the second planet away from the sun. Basically, it's hotter than Mercury, even though Mercury's closer. And the reason for that is because Mercury doesn't have much of an atmosphere. It's too close to the sun. The sun really just boils anything away on Mercury. And so when you get to the backside of Mercury, when it's nighttime on Mercury, it gets very, 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 very cold because there's nothing to hold that heat to the planet's surface. Venus, on the other hand, has this atmosphere of kind of real noxious gases, sulfur dioxide, carbon dioxide, and sulfuric acid. It's a very dense atmosphere, very, very high pressure. And because of this, it has a high greenhouse effect. And just like that greenhouse effect that we talk about in climate change on planet Earth, Venus is a good example of this. All of this stuff compacted in Venus's atmosphere drives that greenhouse effect out of control. And so the temperatures on the surface of Venus are on average close to 860 degrees Fahrenheit. And then, of course, we have planet Earth, and we have some of the defining characteristics of planet Earth. So far, it's the only planet we know that holds liquid water. It sits at a good range for what we know life to proliferate at, somewhere between 0 and 100 degrees Fahrenheit on average. And plate tectonics. So the Earth, we won't get into geology and geography too much, but just a quick rundown. The Earth is composed of a crust, a solid rock crust sitting on molten materials, mainly rock and nickel and iron. So the center of the Earth is very hot and full of these melted down metals and crystals and rocks and stuff. And these plates, these crustal plates, move on top of that melted stuff, and they crash into each other, and they form mountains when they crash, and one might fall under the other when they crash, and this causes volcanoes, and it causes earthquakes, and it causes changes to our landscape. And again, Earth is very unique, and that is the only planet that we recognize this much tectonic activity on. And then finally, we have Mars down there, which is there is some geologic activity on Mars, but not as much as Earth. There's really only ice. There's not a lot of liquid water on Mars' surface. We may see it in very specific circumstances. But regardless, you probably all know Mars is our closest neighbor. It's the next frontier. When and if man makes it further than the moon, Mars will be our next stepping stone. And they're really, NASA and other folks have plans to put people on Mars sometime in the next decade. So we'll see how that goes. It's very, very adventurous. One of the fun things about astronomy is all of the neat pictures you get to look at. So here on the next few slides, I've just got some pictures and a little bit of commentary for you. This is planet Mercury, again, the closest to the sun. this is what an actual kind of telescope image of Mercury will look like, and this is one that's been stylized, if you will, by NASA. They've added some color and stuff. Really, really good pictures there. Here we have Venus. Again, we have a more original telescope image on the left side, and on the right side, we have a real pretty um, color adjusted image, if you will. And this image in the middle, really, really spectacular. This is a composite image from a Russian probe that was sent to Venus in 1988. So this is a picture from the surface of Venus. Really astounding stuff. The probe itself was only able to last for just a few minutes because of the high temperature and the high pressure. All its electronics and even metals and stuff were melted after being on the surface for just a few minutes. But in that short amount of time, they were able to beam back enough information that we were able to bond this image together, and this is the only image we have of the surface of Venus. But really pretty spectacular that we do have that. All right, so on this slide where we might have expected to find a really cool picture of planet Earth, we find a little bit of a joke instead. So here I just want a little bit of commentary, you guys. Lately, a trend has been across social media and other platforms to claim that the Earth is flat, believe it or not. There are some people out there who, for whatever reason, claim to know that the Earth is not round as we've been told, that it's a giant conspiracy, and that the Earth is actually flat. They've produced maps and they try experiments to prove that the Earth is flat, and time again they've just proven themselves wrong. But I want to have a little bit of commentary on this. I think for a lot of these folks, I think a lot of these people are trolling, for a lack of a better term. I think, and in a way, sometimes their message is almost right. Their message is, for a lot of these folks, is don't take anything for granted. See the evidence for yourself. Now, I think they've taken it way too far because I think they've grown. I think some people started with that intention, and now they've grown into this crazy cult of people who truly believe that we're being lied to about the roundness of the Earth. But there's even beyond like having to go to space. There's tons and tons and tons and tons of information um, and evidence for the Earth being round as we depict it. If you would like to have that debate or look at some of the evidence, if you're curious about that stuff, email me, call me, come by, anything. That's something. One of those misconceptions I feel like is maybe dangerously growing around us in social media and stuff. And so, if you want to have a deeper discussion about that, I'm game for that. Just let me know. But like I said, I do want to point out that I think, and I may be completely wrong about this. The original message was, I think, don't take anything for granted. Don't take science for granted. Just because somebody tells you science says something, don't accept that. And that's a good way to live. Learning how to decipher evidence for yourself and determining what that evidence means is one of the greatest tools you can take from science. So, in a way, in a real backhanded way, there's a good message in there. But don't take any of those words. Don't take any of those folks at their word that the Earth is flat. It is not. The Earth is round. So here's just a really good shot of the moon. A little bit of commentary for you there. There is one of the claims that a lot of the flat earthers that we just talked about make is that man has not been to the moon. We did not land people on the moon as NASA claims they did in the 60s. They claim it was a Hollywood production filmed somewhere in the desert, and that basically it didn't really happen. There is a way that or there's a way to gather evidence against that to show that we have gone to the moon. And it was popularized in a well-known TV show, The Big Bang Theory. They showed some of the characters performing this experiment. I doubt they actually did it, but the science behind it was good, and the science behind it actually is true. One of the things that the astronauts did while they were on the moon is they placed a mirror for us to shine a laser beam up and reflect off and um, detect the returning laser beam to measure just how far away from the moon we are and whether that distance is changing. And I'll link in Moodle the scene for the Big Bang Theory so you can watch it for yourself. I've found it on YouTube before, but it's one piece of evidence to show that man has been to the moon and put something up there. It requires some pretty delicate lasers, some pretty expensive detection equipment. So sadly, it's one of those things we can't do with a laser pointer and a cell phone or anything in the backyard. But with enough equipment, you can show that you can bounce a laser off of a mirror that was placed on the moon by one of the astronauts on the Apollo missions. Like I said, I'll provide that link in the clip. Take a look at it if you want, and if you have any questions, let me know. This is a really cool picture here. This is like brand new. This is maybe a couple weeks old, and it's the Mars Perseverance rover put there by NASA. This is not a composite image. This didn't have to be reconstructed. This was beamed straight to us by scientific instruments on the surface of Mars. What you're looking at there, right there, is what the surface of Mars looks like. And if you ask me, that is just the height of incredible. That is just so fantastic, so awesome to know that we're getting these pictures from millions of miles away. Very, very cool stuff. Some more pictures of the surface so you can kind of get an idea of what the horizon and the atmosphere look like. Notice all the red color, just like it appears in the sky. That's due to a lot of rust. There's a lot of iron in the soil on Mars, and so it rusts rather easily with nothing else there to protect it, and that's why Mars appears red. And this is a zoomed out picture of Mars, or maybe a telescopic picture of Mars, really good and clear. I believe that is Olympus Mons there in the picture, which is the largest volcano in the solar system. And here we go. Here are some facts and figures about our outer planets, the gas giants. And I put Pluto in there just for good measure. But really, I listed the 4 gas giants and gave you some information about them. I think the biggest, other than the size and they're being made of gas, one of the biggest differences is the amount of moons that these planets have. Many of them have, the bigger of the two, Jupiter and Saturn, have over 60 apiece, and Uranus and Neptune have 20 or 30 themselves. So, whereas the interior planets have one, if that, the exterior planets, these outer planets, have over 100 between the 4 of them. One of the ones, Saturn's moon Titan, is very interesting to scientists because they think that it has an atmosphere very similar to Earth. They think there's a lot of oxygen in the atmosphere, and that there is a lot of water trapped under some ice there on Titan. So in the future, and when and if we get to planet and we look for other jumping off points to explore the universe, hopefully, Titan may be a good place for materials or just another base or something like that. So very interesting to scientists. Here's a telescopic picture of Pluto. We can see the great red spot there in the middle, which is a gigantic storm that's been observed on Pluto for at least 400 years. Jupiter for at least 400 years. We're not really sure if it's permanent or not, but we just keep an eye on it and try to decide. A telescopic picture of Saturn and its rings. probably the planet most people want to look at, or yeah, the most because of the rings around the outside. Very pretty pictures. All right, and so the last topic I really wanted to cover in astronomy is beyond the solar system. So I wanted to talk about really, this is what I want. I want you guys to just leave this presentation, leave this discussion with some kind of idea about just the sheer size of the universe. This is something that I really like to ponder myself, and so I hope I can pass some of this wonder off to you guys. Some of the definitions that we'll talk about over the next few slides. The first word is galaxy. And so a galaxy is a collection of solar systems kind of in one spot. Usually, a galaxy, these solar systems may rotate or spin around some central point, but galaxies contain millions of solar systems. So that alone makes us feel small enough. So we sit here and we're one tiny speck in this gigantic solar system of 8 different planets. And that solar system itself is a tiny speck in a collection in a collection of millions, if not billions, of solar systems into one galaxy. And then beyond that, there are clusters of galaxies. And then at the very top end, we call everything the universe. And so the best estimate that we have right now, the best estimate that we have right now, I'm trying to see if I can move the, oh, there we go. The best estimate we have right now puts the number of galaxies between 200 billion and 2 trillion in the observable universe. Not solar systems, not planets, but there are 2 trillion galaxies. The universe is enormous, too much for us to even imagine. So, one of the concepts I would like you to understand from this discussion is that of the light year. Light years are a measure of distance, not speed or time, as they're often confused with. The distance that a light year covers is the amount of distance that light can travel over the course of 1 year in a vacuum because it moves faster in a vacuum than anywhere else. So the way you can think about this is if you were to take a trip to space and you had a flashlight with you, you turn on that flashlight and you held it in the same spot for 1 year. However far that light from that flashlight reached in that year span would be 1 light year. You can see that it is equivalent to about that many miles that you see there on the slide. Large number. It may be 58 trillion, it may be 587 trillion. It is a large amount of distance. But things in the universe are that far away. In fact, they're much further than 1 light year. One of the most mind-blowing things I think science has made me think about is this. And I'd love to have this discussion. I wish I could have this face to face with you guys. It's a pretty simple concept, but it makes you feel small. So some of the stars, if you look at going outside at night and you look up in the sky and you see all these stars, those are probably, if you think about it pretty easily, obviously to think about, those are the closest stars to us. That's the reason we can see them, is because they're the closest. Some of those, Betelgeuse, in fact, you can look up the name of the star, Betelgeuse, is about 640 light years away. Okay, so if you shined a light, if you took a flashlight and pointed it at Betelgeuse, and turned it on, it would take 640 years for your light to strike that star. In reverse, what that means is this, and this is the mind-blowing component to me. Let's say you look up at Betelgeuse, you go into your backyard at night, and you look up in the sky, and you locate. You can use there's some really neat phone tracker apps, by the way. Different astronomy. Sky Map by Google is a good one that will help you locate. You can hold your phone up to the sky, and it will help you locate different constellations and stars and planets and stuff. So if this stuff interests you, download one of those. They're a lot of fun. But back to what I was saying. So if you go out, maybe you located Betelgeuse using one of these apps and you looked at it, you'll notice that most stars have a slight pulse or twinkle to them as different events happen on those stars. They get brighter or dimmer, yada, yada, yada. Well, what's interesting to me is if you go out and look and you see, let's say you see Betelgeuse twinkle. Well, Betelgeuse is 640 light years away. What that means is that twinkle, that those photons reaching your eye, actually happened 640 years ago. So in a way, it's kind of like looking back in time. Maybe that doesn't blow your mind as much as it does mine, but I really, really find that interesting. It's something I think about often. Here on this slide, we have the organizational hierarchy of different structures in the universe. And it basically just flows like this. They use Earth as their example. So planets are organized into solar systems. Solar systems are organized into galaxies. Galaxies are organized into groups of galaxies. Groups of galaxies are organized into superclusters, and then the superclusters is then organized into the whole universe. So that's just a description of the different hierarchical structures of astronomy. Here on this slide, we have a depiction of the galaxy that we call home. So Earth is a member of the Milky Way galaxy, and you can see they have here on the picture, they have our sun depicted in its position in the galaxy. And again, this is just to give you kind of an idea of the scale of the universe. So our sun and consequently us and the other planets would be located about right here. All of these other dots, light that you see are stars, and each one of those stars is very likely to have its own solar system. So just within the Milky Way galaxy, again, you can see that there are millions of stars and solar systems, and that is just one galaxy. And here we go. This is the close of the presentation. So earlier in the semester, at some point, I had linked a video. There's a video, and you can go look it up if you want to. Go to YouTube and type in the greatest picture ever taken, or the most important picture ever taken. And this slide is a selection from that video. What you see in this slide, this was taken with the Hubble Deep Field Telescope. Every dot of light that you see there is not a star. Each one of those dots of lights is a galaxy, just like the Milky Way. Each one of those dots that you see there contains millions of stars and millions of solar systems. And then what was interesting about the video is what Hubble found was this is just the surface image. This is the image it was taking anyways. Well, researchers wanted to find what was in these black spots. If the universe is so full of these galaxies and planets and stars, what's in these black spots? So they pointed the telescope at the black spots, and what they found was essentially the same picture. If they went deeper and deeper and deeper, they found essentially the same picture over and over and over again. So these galaxies and the amount of stuff in the universe just stretches on for what seems like infinity to the human mind. And it's very mind-blowing stuff. I find it very, very interesting. Some objects in the universe are as far away as 114 billion light years. So even if we could travel at the speed of light, which we're nowhere close to, it would take us 114 billion years to get there. We may never make it. to the other side of the universe. Um, I hope you enjoyed this discussion. If you have any questions about anything that I talked about here, this is a subject I really like to discuss and debate and talk about and think about. So, and that goes with most of the science stuff that I've done in this class, but but this one in particular, astronomy has always held a really close place to my heart. I think looking up in the sky at the planets may have sparked my whole interest in science when I was little. So I love discussing this stuff. Please let me know if you need any help or would just like to ask any questions.